Hello, good morning my dear students. I am Anjaneyulu, working as physics lecturer in one of the reputed institutions in Hyderabad. Today we are going to discuss very important concept for all competitive exams. Okay, so NEET means advanced level. Definitely you will be given one question based on this concept. So that is about a capacitor. Okay, so capacitor is an electrical device which can store lot of electrical energy in a small space. Okay, so a device which stores electrical energy in a small space. So I'll give you one small example to know about capacitor. So usually, when there is no starter in the tube light, when you switch on, it will take a lot of time to put on. Suppose if you are using a starter, definitely once you switch on, immediately light will put on, right? So we can say it will be providing electrical energy immediately. Okay, so you require capacitor to run a fan, to run a tube light. So most of the electrical devices are running based on this capacitor. So today we are going to know how a capacitor is capable of storing a lot of electrical energy in small space. Okay, so to know about this, let us consider a plate, okay, having uniform thickness, has given a charge, say Q. So this capacitor has given a charge Q, say plate A. So I have taken one plate A which has given charge Q. Okay, so as you are giving charge to your body, automatically the level inside the body will increase. Charge level will increase. So that is you call potential. So when you are giving more charge to your body, its potential will also increases. So Q proportionate to V. Okay, or Q by V gives a constant called proportionality constant, or it is also called capacitance. So capacitance of capacitor C is defined as charge given to potential raise. So the more charge you give, the more potential it will show. Just like you take one glass, pour some water. So the moment when you pour some water, water level will increase. Similarly, the more charge you are giving to your body, its potential also increases. So that ratio is called capacitance. Okay, so charge units are coulomb, okay, and potential units are volt. Now coulomb per volt, or it is also taken as farad, denoted by letter F. Remember, farad is the unit of capacitance. Okay, so a device which stores a lot of electrical energy in a small space is called capacitor. So the formula which we are using to find capacitance is Q by V. Okay, charge given to potential rise. So you already know, when you are giving charge to your body, automatically the level of charging, right, Q you are giving, so potential will also increase. So that ratio, so constant, it does not depends on Q and V. It only depends on the size and shape of the condenser you are using and the space between them. Nothing but you can say dielectric. Okay, not depends on Q and V, because the ratio remains same only, however you change Q and V. So it mainly depends on dimensions of the geometrical shape of the condenser and also the medium between the plates. Okay, now you have taken one plate A which is provided with an insulator and it has given a charge Q, then its capacitance is C equal to Q by V. And how you measure capacitance? Remember, farad. And the symbol of capacitor is two parallel plates. Okay, now, so capacitance is Q by V in the beginning. Okay, now we are going to know how to increase the capacitance of a condenser. Very simple. That is, you place another plate B nearer to it. Okay, so you are placing an uncharged metal plate B nearer to A. So thereby due to induction, one side negative is developed, the other side positive is developed. No, so whenever you are bringing another metal plate B nearer to A, due to induction, one side negative is developed, the other side positive. Suppose if this plate N is connected to ground. Okay, so thereby that positive charge also transferred to ground, called earthing. No, earthen capacitor. So whenever this connected to ground, so automatically all this positive charge will transfer into earth. Okay, so why we are bringing a plate B nearer to A, that is in order to decrease the potential of A. We are bringing a plate B nearer to A. So thereby its potential decreases. Followed by capacitance increases. Same charge but potential is reduced. That means what about this negative? So this negative engaged with positive. That means this negative charge effect is more on this plate A. That means it is trying to reduce the potential of A, right? Thereby the net potential decreases. So whenever you are bringing plate P nearer to A, so the net potential decreases, followed by capacitance increases. So in this way it's very easy to reduce the potential. But remember, capacitance of a capacitor depends upon area of the plate, distance between the plates, and the dielectric between the plates. You please watch till end of the video. You are going to definitely get confidence about capacitors. Okay. Now we are going to know about capacitors in series combination, or you can say capacitors or condensers in series combination. Okay, now we are going to find the effective capacitance when they are joined in series combination. Okay, so capacitors or condensers in series combination. Okay, so today we are going to know about capacitors in series combination. So whenever capacitors are joined, okay, in series combination, charge on each one remains same. So very important point under this derivation, that is whenever capacitors are joined in series combination, charge on each one remains same. Okay, and potential difference is divided. Suppose if the ends are connected to a battery, voltage across first one or second one, third one changes because they are having different capacities, no? So that is why whenever capacitors are joined in series combination, charge on each one remains same and potential difference divided. So how you know they are connected in series combination? That is, every capacitor is having two parallel plates now. That is, second plate of first one connected to first plate of second one, right? And second plate of second connected to third of first plate. Okay, so in this way they are connected in series combination. Okay, so you know formula for C, ratio of charge given to potential rise, gives C, right? So in this series combination, now charge remains same. That means Q equal to C1 V1, or it is also equal to C2 V2, or it is equal to C3 V3. So remember, whenever capacitors are joined in series combination, product of CV remains same. Okay, so C1 capacitance of first one, right? C2, C3 or capacitance of second and third. Okay, so V1 is potential difference across first one, second one, third one. Okay, so you know total potential difference is equal to sum of the differences. Okay, so suppose if the endpoints are connected to a battery now, then say that total voltage supplied is V, then across first one V1, second one V2, third one V3. So you know total potential difference is equal to sum of the differences, right? So you know V1 is equal to, you know, C Q by V naught, then V becomes Q by C, right? So Q by C1. So this is the potential difference across the first one. Okay, second one Q by C2, because you know in series combination charge on each plate remains same, right? V3, you know V3 equal to Q by C3 now. So V1 you know Q by C1, V2 Q by C2, V3 Q by C3. Okay, so total potential difference is equal to Q by C effective. For our convenience, take it as CS. So CS is the effective capacitance of these capacitors. Okay, so while grouping series now, remember effective capacitance taken as CS. Okay, so Q by CS is equal to, okay, V1, you know, Q by C1 plus second one Q by C2, third one Q by C3. So what do you notice? Q is common, right? So Q, if you take common now, so effective capacitance, so 1 by CS is equal to, you know, 1 by C1 plus 1 by C2 plus 1 by C3. So remember, whenever you join capacitors in series combination, so the effective capacitance offered is always less than the capacitance of capacitor. That means you can say it is offering minimum capacitance. So these are the points you need to remember under series combination. What are they? Whenever you join capacitors in series combination, they offer minimum, okay, or least capacitance. Okay, and charge on each one remains same. Okay, potential difference, say V divided. Okay, so in this derivation you have taken three different capacitors which are joined in series combination. So you know charge on each one is same now, so that is why potential difference is divided. V equal to V1 plus V2 plus V3. Okay, so V1 means potential difference across first one, second one Q by C2. No? So when you substitute now by taking Q common, Q gets cancelled. You get effective capacitance, right? 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Okay? Suppose you have taken identical capacitors. Say the capacitors are having equal capacitance, right? So, C1 equal to C2 equal to C3 now. That is in case of identical capacitors, all are having equal capacitance, right? So, 1 by Cs is equal to 1 by C plus 1 by C plus 1 by C. So, 1 by Cs is equal to 3 by C, right? So, Cs becomes C by 3. In this case, that is when you have taken 3 identical capacitors. Instead of 3, suppose you have taken n, then Cs is equal to C by n. Okay? Now, about capacitors in parallel combination. Okay? So, how to find the effective capacitance when the capacitors are joined in parallel combination? That is, suppose you have taken 3 different capacitors, say C1, C2, C3, okay, joined in parallel combination. That means all the positive plates of capacitors are connected to one point. All the negative plates of capacitors are connected to another point. Then they are said to be connected in parallel combination. Okay? Now, in case of parallel combination, remember, potential difference across each capacitor remains same. Okay? So, whenever capacitors are joined in parallel combination, potential difference across each one remains same over there, whereas in series combination, charge on each one remains same. So, in case of parallel combination, you need to remember that potential difference, okay, across each capacitor remains same. Okay, so potential difference across each capacitor remains same and Q is divided. Okay, over there, charge is same, V divided. In parallel combination, remember, V same, Q divided. So if you know this easily, you can derive the derivation. C is equal to C is equal to, Q by V. Now, C equal to Q by V now, then, V same now, so Q1 by C1, right? Or it can be taken as Q2 by C2. Okay, or it is equal to, Q3 by C3. So remember, whenever capacitors are joined in parallel combination, potential difference across first or second or third remains same. Okay, so Q is divided now, that is, total charge is equal to sum of the charges. Now, total charge is equal to sum of the charges. Q equal to CV, no? Means C effective. For our convenience, take it as CP. So CP means effective capacitance of this combination into V. Okay, so Q1 means charge on first one. Okay, so charge on first one is C1V, right? Charge on second one. Okay, so charge on second one is, C2V, right? Charge on third capacitor is C3V. Okay, so total charge Q taken as CPV now. So CPV is equal to, C1V plus C2V plus C3V, because Q equal to Q1 plus Q2 plus Q3 now. So V common now, you can cancel. Okay, you can cancel. Therefore, effective capacitance, right, in parallel combination is given by C1 plus C2 plus C3. Okay, so remember, whenever you join capacitors in parallel combination, first important point, that is V remains same, means potential difference, right? Q divided and offers maximum capacitance. Okay, so capacitance offered by them when they are connected in parallel gives maximum. So maximum capacitance offered when they joined in parallel combination. Suppose you have given two capacitors. So if you join them in series, they give minimum capacitance. If you join them in parallel, they give maximum capacitance. Okay? Next. Suppose you have taken identical capacitors. Say all are having, say, equal capacitance, say C. Okay? Then capacitance, okay, when they joined in parallel combination is, Cp is equal to, right, C plus C now, that is when 3 are connected, so it is 3C. Suppose instead of 3, say you join n capacitors, then capacitance offered is Nc. Okay, so remember, when n capacitors join in parallel combination, capacitance of the total combination, say grouping, is Nc. Okay, so remember, capacitors you can join in two ways, two groups: series combination, parallel combination. In series, Q same, V divided. In parallel, V same, Q divided. Series offers minimum, parallel offers maximum. Okay, about parallel plate capacitor. So concept is about parallel plate capacitor. Okay, so let us consider two parallel plates, okay, of area A, okay, separated by a distance, say D. Okay, so one has given a charge, say Q. Okay, a positive charge is given to plate 1. Okay, and the other one is, say, connected to earth. Then due to electrostatic induction, that is, we all know, one side negative is developed now, so negative is towards the positive one, right? And the plates are having uniform area now. So that is why the electric field, see the electric field between the plates is also uniform. Okay, so the electric field between the plates is also uniform, right? Now let us introduce a dielectric constant K, okay, between the plates, fully filled without leaving any gap. Okay, now you want to know the effective capacitance. So you already know in the previous concept, that is to find electric field strength now, we are using formula, that is C is equal to Q by V now. So what is general formula we are using to find the capacitance of a condenser or a capacitor? That is C is equal to Q by V. That means to find capacitance of a condenser, you require charge on it and also potential difference between the plates. So here charge is known to us, so only you want to find potential, right? So potential is related to electric field strength now. So before going to find potential, you need to find strength of electric field. Okay, so electric field strength we can also find by using Gauss law. Remember, electrical flux is equal to line integral EDS. Okay, electrical flux is equal to line integral EDS. No, so line integral EDS equal to electrical flux, which is taken as Q by epsilon naught. That is when there is no medium. No, over here you are placing it a dielectric medium now between the two plates. So that is why that influence is also taken, right? So that's why Q by K epsilon naught. Okay, so E A is equal to, okay, Q by K epsilon naught. Okay, or E taken as Q by K A epsilon naught. Okay, take it as equation 1. Okay, suppose if there is no medium between the plates, say only air is the medium, that means K value will be taken 1 now. So if K equal to 1, that means air is only between the plates, then K taken as 1, and E is equal to Q by K taken 1 now, so A epsilon naught. Okay, so electrical potential V equal to ED now. So this Q by A epsilon naught right into D. Okay, so that is V. So what is general formula for C? C is equal to Q by V. No, C equal to Q by V. Okay, so C is equal to Q as it is. Instead of V, I am writing Q by A epsilon naught D. Na? So Q cancelled, you get A epsilon naught by D. That is when air is the dielectric between the plates. Okay, so when air is the dielectric between the plates, what is formula for parallel plate capacitor? A epsilon naught by D. Okay, suppose it is fully filled with a dielectric. Okay, then this K we keep as it is now. Then it is Q by Ka epsilon naught into D, right? So this K coming into numerator. So what is formula for parallel plate capacitor when it is fully filled with a dielectric, that is Ka epsilon naught by D. From this we can come to a conclusion that capacitance depends on area of this plate, right? Distance between the plates and also the dielectric between the plates. Okay, so now we are going to know if you are filling partially instead of fully filled between the plates, let us fill the dielectric partially between the plates. Okay. Okay, so now I am taking a dielectric. Okay, I am taking a dielectric between the plates of thickness T, dielectric constant K. So here it is partially filled, not totally filled. Okay, so you know electric field strength, which is uniform now, because plates are having uniform thickness, uniform area, right, and it has given a charge Q that is uniformly distributed, so that is why electric field between the plates is uniform, and that you know it is Q by Ka epsilon naught. Okay, but now you are introducing partially, no, so that is why the distance changes. So dielectric placed thickness T na, and the remaining distance you know D minus T. Therefore, you know the potential changes. Na? So potential is equal to you know ED. Right? So there is some electric field at dielectric, means potential inside this plus the other remaining place. Right? So strength of electric field into this corresponding thickness taken as T plus, okay, the remaining distance, that is you know D minus T. Okay, so E inside means you know Q by K A epsilon naught into thickness na plus the other part you know Q by, over here dielectric is air na, the remaining space air na, so that is why that dielectric constant value taken 1, right, into A epsilon naught of D minus T. Okay, Q by A epsilon naught of D minus T. Okay, now this is about potential. So you know how to find the capacitance, right? Formula for C is always Q by V na. So Q is charge on each plate, right, by potential. So just now you calculated. So here if you notice Q by A epsilon naught is common na. So Q by A epsilon naught taken common, then you get T by K, right, plus D minus T. Okay, so Q gets cancelled, right? The effective capacitance between the parallel plates when they are filled partially like this. Okay, then you know C dash, or C you can take, is you know A epsilon naught, okay, by D minus T plus T by K, where T, you know, thickness of this medium, the one which you have placed between the plates, thickness, and K its corresponding dielectric constant. The remaining is air only now. Now, so this is the formula. Okay. Suppose if you are placing a metal, okay, between the dielectric plates. So whenever you are placing metal in between the plates now, then you know dielectric constant for metal is always infinity. Remember, whenever you place a dielectric metal, okay, in place of dielectric, place a metal between the two plates, okay, then you know K value will become infinity now. When a metal of dielectric constant, you know, for a metal dielectric constant value is infinity, okay, placed between the plates, okay. So this is infinity now, then this whole thing will become 0, right? Because anything 1 by infinity is 0 now. So you get C, capacitance between the plates, that is when you are placing a metal between the two plates, you get A epsilon naught by D minus T. So all these formulas are very, very important. So under this you need to remember that C depends on area and distance of separation and also dielectric between the plates. Now let us discuss, that is when you are placing side by side a dielectric or one upon other dielectrics, how its capacitance changes. Okay, so for all, you know, we have to use only one formula. Okay, that is C is equal to K into A epsilon naught by D. That is K is the dielectric constant, right? Now, let us take in between the plates two dielectrics. Okay, so I am taking two dielectrics in between the plates, okay, in this way. So if you notice, distance occupied by first dielectric or second dielectric is same, right? But area wise divided, no? Half area first dielectric, remaining half area of plate second dielectric. Okay, so if you notice this, it is easy to solve this problem. So in order to solve the effective capacitance when two dielectrics are kept in this way, what we supposed to do? Divide this into two capacitors. Okay, so you know C is equal to, right? C is equal to K A epsilon naught by D na. Now this is you divided into two dielectrics na. So that's why C1 equal to K1. Area wise, if you notice na, half area is only divided. So that is why A by 2 epsilon naught. But distance wise no change. See, distance remains same. And K1 A epsilon naught na by 2D. Okay, next one, C2. So K2 A epsilon naught by 2D. Okay, so these are the two dielectrics you have taken. Now you want to find effective capacitance. If you notice, the end points of the dielectrics are same now. So nothing but you can say they are in parallel combination. Remember one valuable important point while you are solving problems, that is whenever the end points of capacitors are same, then they are said to be connected in parallel combination. Okay, so here two capacitors, now endpoints are same, that means they are in parallel combination. So you know whenever you join two capacitors, right, in parallel combination, effective capacitance is C1 plus C2 na. So that is why these two must be added. Okay, in order to find effective capacitance. So here K1 A epsilon naught by 2D, right? Second one K2 A epsilon naught by 2D. Okay, so A epsilon naught by D, if you are taking common, you get K1 plus K2 by 2. So this can be taken as C, means initial capacitance. Okay, so C effective is equal to initial capacitance, that is when there is no medium between the two dielectrics. So when there is no medium between the plates, when these two dielectrics are not there, okay, then it is C. But whenever you are placing a dielectric between the plates, okay, so whenever you are placing the dielectric, this is the formula for effective capacitance. Okay, so in this way you can also find the effective capacitance when dielectrics are kept one after the other, side by side. Okay. Okay, now you have taken two dielectrics side by side. So in the previous case, when you are placing in this way, area divided. Over here, it's very clear that distance is divided, no? But area wise, same only, no? So in this problem also, we divide these two into two capacitors, then we find the effective capacitance. Okay, now, so for all problems, remember C effective taken as always K into A epsilon naught by D. Okay, so here area same, only distance divided. Say half of distance with one dielectric, remaining half with another dielectric. Okay, so C1. Okay, C1 taken as K1, right? Area wise same epsilon naught by D by 2. Why? Because half of the distance placed one dielectric. Next C2, okay, K2 A epsilon naught by D by 2. Okay, so now these two capacitors, that is you have to treat them as two capacitors. So remember, when only one joint is same, or here only one joint is common for these two. In the previous one, two joints are same. That is why you have taken parallel combination. But over here, only one joint is same. That means it's very clear that they are joined in series combination, right? So whenever two capacitors are joined in series, C1, C2 by C1 plus C2. That is, 1 by Cs is equal to 1 by C1 plus 1 by C2 now. So that is why when they are joined in series combination, C1, C2 by C1 plus C2. Okay. So already we know that these two are divided into two capacitors, right? So effective capacitance, okay, is C1, means first one 2 K1 A epsilon naught by D. Okay. To K1 A epsilon naught by D, right? Into second one, 2 K2 A epsilon naught by D. Okay, by C1 plus C2, means 2K1, right? 2K1, or else you can also take A epsilon naught by D also common. Okay, So A epsilon naught by D into 2 if you take common, okay, you will get K1 plus K2. Okay, so 1 A epsilon naught D D2 are cancelled. Okay, so you get K1 K2, right? 2 K1 K2. Okay, by K1 plus K2 into 1 A epsilon naught by D is left na, that can be taken as C. Okay, that is when there is only air is the dielectric between the plates. Okay, so when there is no medium between the plates, capacitance, C. Okay, so this is the formula we are using, that is when you place two dielectrics side by side. Okay, so when you place side by side, distance divided, one upon another, area divided. So if you remember these two now, easily you can solve the problems. And one more important point is, whenever two joints of capacitors are same, parallel. When only one joint is same, series. Okay. Now about energy stored in capacitor. Energy stored in capacitor. So now we are going to know about energy stored in a capacitor. So every capacitor is capable of storing some charge. So work done in storing charge itself gives its energy. Okay, so work done in storing charge itself is energy of capacitor. For example, you have taken one capacitor, Q is charged on it at any instant. Okay, and suppose you are giving dq charge to it. Okay, so when you are giving dq charge to it now, so certain amount of work is to be done. No, because you are giving small charge to the capacitor. So work done in the process, okay, is equal to potential into charge now. So dW is equal to VdQ. Okay, and V potential, potential is equal to Q equal to CV, or V taken as Q by C now. Okay, so potential substituted as Q by C. Okay, so work done is equal to, okay, Q by C into dq. But this is a small work done in giving dq charge. Let us suppose the capacitor is charged up to capital Q. Then work done now in between 0 to Q will give us the total work done. No? So when you are integrating between the limits 0 to Q, you are able to get the total work done. Okay, so work done is equal to, while integrating, always you take constant outside now. So Q power 1 dq between the limits 0 to Q. Okay, so integration formula, x power n dx is always taken as x power n plus 1 by n plus 1 na. So here power is 1 na, so you get q square by 2. Okay, so 1 by c into q square by 2 will give us the total work done. So it is equivalent to energy now, because already capacitor is charged up to Q. So it is in the form of storage energy, right? So work done equivalent to energy, no? So potential energy or storage energy of capacitor is Q square by 2C. Or Q CV na, you can also change this into C square V square by 2C. So 1C cancelled now, you get energy in other form is half CV square. So remember, total energy stored in the capacitor is Q square by 2C, or else you can also write half CV square. So this formula we use when C and V are known. Over here Q and C are known. So depends on the problem, we use formulas, right? So energy stored in the capacitor is nothing but the amount of work done in storing the charge. Now we are going to know special cases under this. Okay, so there are two special cases under this. So IP point of view also, this derivation is very important one. Okay, so now we are going to know the two special cases about energy stored in capacitor. First special case. Okay, special cases. So let us suppose we have taken one capacitor, okay, of capacitance C. Okay, now you place one dielectric, okay, so it is filled with totally a dielectric of constant K. So plates are filled, the space between the plates is filled with a dielectric and it is connected to a battery. Okay, so what is first special case? A dielectric is kept between the plates, okay, and connected to battery. So you know very well, whenever you place a dielectric, the effective capacitance will increase now. So that is nothing but K times of C. So it is connected to a battery. That means it will be go on charging. That means Q is changing, no? But there is no change in the potential difference between the ends of battery or between the plates of capacitor. So potential difference remains same because they are in parallel combination, no? So PD, potential difference remains same. So here we know V and C. So whenever these two are known, we can use one formula for energy stored in capacitor, half CV square instead of Q square by 2C. Why we are not using that formula? Because when you are connected to a battery, charge will go on changes, right? So that is why we are using this formula, half CV square. Initial energy. Now the final energy is half C dash V square. No change in the potential now. So that is why U dash is equal to, means final energy when you are placing a dielectric between the plates and connected to battery. Okay, so C dash taken as Kc na into V square. That means K times of half CV square. Means energy increases by K times when the capacitor is connected to a battery and the space between the plates is filled with a dielectric. So this is one case. Okay, now about second case. That is, say it is disconnected from a battery and the space between the plates is filled with dielectric. Okay, so now about second case. Okay, so that is the space between the plates is filled with a dielectric, okay, and it is disconnected from battery. So whenever you disconnect from a battery, so it stops charging, right? Means Q remains same. Over there, potential difference remains same. But in this case, charge remains same. Okay? So whether you disconnect or connect, between the plates is filled with dielectric now. So that's why capacitance will increase. Means K times of initial. Now think over it. C known, Q known. So we use another formula for energy, that is Q square by 2C now. We are not preferring now this half CV square. Why? Because when you disconnect it from the battery, it stops charging. No? So that's why Q remains same but potential changes. Right? So Q square by 2C. Now initial. Now final. 2C dash. Right? So U dash means final energy when it is disconnected from battery. Right? So Q square by 2C dash now, that is taken as 2 times of Kc. Right? So instead of Q square by 2C you can write initial energy now. So that's why energy by K times. Means it's very clear that whenever you stop charging, right, disconnected from a battery, then further cannot be charged, right? So that is why energy definitely decreases by K times. Okay. Now about the given problem. You have given 3 identical capacitors are connected in this way. Okay. So you want to find the effective capacitance between A and B. Okay, when these joints are not given, it is very clear that they are all joined in series combination. But you have given now some joints. How to solve such problems? Very simple. That is, you give numbers to the endpoints of capacitors. Over here, how many capacitors you have given? 3, right? So 1, 2 endpoints of first capacitor, 3, 4, okay, 5, 6. Okay, now endpoints of first capacitor 1 and 2. So if you notice, this 1 end is given to where? 5 and 4, common, no? That means this 1, 4, 5 are at one end, right? Now, if you notice, this 2, 3 joint is given to 6. That means 2, 3, 6 are at another side. Okay, so between 1 and 2, you need to connect one capacitor. Connected, no? Next, between 3 and 4 also, there is one capacitor. So if you notice, 3 is right side, 4 is left side. Okay, next, between 5 and 6 also, you need to connect one capacitor. So 5 left side, 6 right side. So, they are all connected in parallel combination. Whenever endpoints are same now, they are said to be connected in parallel combination. So you already know, whenever you join n identical capacitors in parallel combination, it is n into C now. So here you are connected 3 capacitors. So that is why the effective capacitance becomes 3C. We are going to solve a problem about infinite ladder network. So what is infinite ladder network? So in this circuit, capacitors are connected in a repeated manner up to infinity. Okay, such networks you call infinite ladder network. Okay, so here you see C1, C2. C1, C2. So in this way, it is connected up to infinity. So whenever capacitors are connected in a repeated manner, they are said to be connected in infinite ladder network. So based upon this also you can expect one problem in competitive exams. So very simple. That is same capacitors are repeated now. So what we supposed to do, first you take this first loop. Only first loop I am taking. Okay. So whenever the same capacitors are repeated, then you know the end points of this you take it as equivalent capacitance. See, over here also equivalent capacitance. So it is modified circuit. Okay, whenever you have given in this way infinite ladder number, so you modify into this way. Okay, now, so if you notice these two are in parallel combination, right? So you may be given this as say 1 microfarad, this is 2 microfarad, or you will be given 5, 10 or 10, 5. Okay, you will be given some values no for C1 and C2. Then first these two you take it in parallel combination. You see the end points are same now. So this is C. So C1 plus C plus C2. This is C1, right? Now if you notice, these are all again in series combination now. So 1 by C is equal to, okay, 1 by C1 plus 1 by C plus C2. That's all. So you put C1 and C2 values, find C. Okay, very simple. Thank you student, that's all for today. So I request all of you to subscribe my channel, so to give more and more updates in NEET, JEE mains, advanced level. Okay.